So before we go on and learn more about this wonderful world of NMR that's going to make your life miserable for the next 2 weeks, or maybe the next week, I want to show you what we're actually using in a laboratory environment. This whole concept of, hey, let's put in a compound and let's get these lines on a sheet of paper. Where is that actually coming from? Well, where it's coming from is something that looks like this. This is an NMR, a nuclear magnetic resonance instrument. And this NMR machine is just one example of many different variations and versions that might be out there. There's tons of different variants of NMR. All right, so NMR in this picture, it's actually as tall as a person. So this is located in a room. You can see the drop ceiling lights and the fluorescent lighting up above it. But this instrument is massive. It is probably one of the largest instruments that we use or that we work with in a laboratory on a routine basis, if you call it a routine basis. So this instrument is made up of a couple of high powerful magnets, and you're seeing these magnets kind of housed in this chamber or this container. And of course, all of the cables down below are meant for different purposes. We're not going to get into that. It's not all about how the machine works and the gears and the mechanisms that kind of get it to do its job. But this instrument does do a job, and that is based on magnets. That's the most important part of this process. So we're often going to see NMR instruments that are very large in a room, and because this is magnetic, or it works off of magnetic properties, very often these are in their own room. All right, so they have their own dedicated space. They do not share it with anyone else. We try to keep computers and any electronic devices away from them if that's possible as well. So we see the NMR actually part of the machine that makes it work in a dedicated area, and those cables typically are fed into a computer system that might be present in a completely different room. And this is what I would call the big boy NMRs, all right, or the big girl NMRs. So these big instruments are more for research and development type of purposes, industry, universities maybe that are doing some research and development type of things. However, we know that something like this is not very applicable into an academic setting. And because of that, we have a different variant or version of NMR that you might see in a laboratory, and it could look like something like this. They are very tabletop. Notice the computer is basically right beside of them. These are not massive. They fit on a countertop, as you see in the picture. That also means that they're not large magnets that get these things to operate, which is why you see the computers nearby them. This is just something a little bit more convenient, not very high powerful. These instruments are wonderful for academic type of purposes, or maybe for purposes that don't need the bells and whistles that a big normal R&D NMR will bring with it. These are typically kind of expensive. If you take a look at the NMR that is kind of what I would call traditional scale NMR, these machines will cost anywhere from $500,000 to $1 million or more, depending on what you need and what kind of capabilities that you want with it, where the benchtop NMRs will just basically come with a pretty simplified magnetic system with computer and software, nothing special here, and these are normally $50,000 to $60,000. So that gives you kind of a price difference between them. So in terms of academic purposes, these are pretty great. This instrument, just like the other instrument, it needs a sample, and the sample entry ports are typically, lowered from the top or some type of door that will open up. So we're going to eventually put these organic compounds into an NMR. We're going to close the door, kind of seal it off, and then we're going to allow the NMR to do what the NMR needs to do. So I think it's very important for you to take a look at these pictures of NMR instruments. What is actually doing the measuring, what's doing the analytical parts of the NMR for us, and I think these pictures kind of get that point across, hopefully. So at this point, we've talked about NMR and the protons and how we can get basically different signals from a compound based on the number of types of hydrogens that we have. So keep in mind, we're talking about hydrogen NMR, right? That's what this is all about, HNMR. So like we've said in a previous video, if I've got a carbon with 4 hydrogens on it, all right, so there's 1 hydrogen, there's 2 hydrogens, there's 3 hydrogens, and there's 4 hydrogens. If I've got this carbon with these 4 H's, and we're given the question of, well, how many signals will an NMR give you based on this molecule? You're going to look at this and you're going to go, well, all right, I'm not really comfortable maybe doing this right off the bat, so I'm going to do what Mr. Tracy told me to do. I'm going to erase one of the hydrogens and I'm going to replace that with something like a halogen, so something simple like a bromine. And I'm going to name it. So if I take the name of this structure, it is 1-bromo. Actually, I don't even need the 1 because there's only 1 carbon there. And 1 carbon chain is methane. So bromomethane is what we're going to call this because there's only 1 option there. So if I want to know, well, what about these other hydrogens? Do they give me different signals? Because we're talking about H and MR, and I need to look at different H's, and there's 3 different more H's on here. What am I going to do? Oh, God. Well, that means I'm going to erase this bromine, and I'm going to replace it back with what it was, and that was a hydrogen, and then I'll just target another one. It doesn't matter. I'll do the one over here to the right-hand side, and I'll put a bromine there. And I'll look at that molecule, and I say, all right, well, is that a different name? So if I asked you on a test question, what is the name of this compound? You're going to give me the same exact name that you wrote down with the previous one, and that's bromomethane, because there's only 1 bromine on it, and there's only 1 carbon, and there's no difference as far as the names go. So this is the same signal from that hydrogen that's from the previous hydrogen that we deleted, and it would be the same signal as here, and it would be the same signal as there. It's all the same name, which means it's equivalent hydrogen. And if we're talking about equivalent hydrogens, then that means they're all the same signal. It's just the intensity or the height of the signal that's going to be a little different. So how many NMR signals do we get? And the answer is 1. So this is where I want to pick up from. I want to pick up from this concept of how do we determine the actual number of different signals that we will get from the compound, right? Before we go any further, before we talk any more about NMR, this is something that we've got to get down, because if we can't get the total number of signals down, well, forget everything else, because I'm going to fail it, and I'm going to fail it with flying colors if I can't figure out how many different signals I'm going to get from compounds. So we need to do example problem after example problem after example problem after example problem. So the problem they're going to give me here is this benzene ring. Oh, I remember benzene lectures. Those were like months and months ago, right? So we get these benzene ring with this CH2CH3 group off of it. Can you name this structure? I hope you can, because we've learned that this semester. So I'm going to look at the ring and I'm going to call this, hey, it's a benzene. And then off of this benzene ring, there's a CH3CH2 group. What's that called? The 2-carbon chain. That is a ethyl group. So ethyl benzene is the name of that structure. So I'm going to take ethyl benzene and I want to know, how many signals will I get from this thing? If I put this into an NMR, do I get 1 signal? Do I get 2? Do I get 3? Do I get 4? Who cares about anything else? I don't really care what else the NMR is going to bring to the table. I just want to know how many different types of signals, which means how many different types of hydrogens do we have in this molecular structure. All right, so just like before, I told you, if you're uncomfortable, do it this way. So we're going to draw the structure, and I'm going to go, I'm going to get rid of that hydrogen and put a 2 here, and then I'm going to draw where that 3rd hydrogen would have been. I'll just replace that one with a bromine group. All right, and I would name it. And then I would do it again. So here's CH3 and CH2. And then here is the benzene ring. And then I will do my get rid of that hydrogen and replace that hydrogen with a bromine. Is that different? Well, you're going to immediately look at this. We're not going to name it. You're going to immediately look at this and you're going to say, yes, that is different. Right? I've got in the first example bromine on the end, and then in the second example I've got bromine in the middle, and that's going to be a different name because it's in a different position, because the molecule is not symmetrical. So yes, these two things are going to give me different signals, and you're going to say, the answer is 2. And I'm going to go, no, it's not. Actually, there's more signals than this, and that's because you fell for the trap. And what you fell for was the not writing it down, meaning that this benzene ring, that has a carbon, and one of those carbons has a double bond. One of those carbons has a single bond. Remember, it's an alternating double, single, cause you trouble. And then off of each one of these carbons, folks, don't forget, there are hydrogens here, right? Off of each one of these. So if you made the mistake because you didn't see hydrogen drawn, you need to keep in mind that sometimes people are a little lazy with their structures and they're not going to draw you every single hydrogen on a molecule. That's up to you to do, because you should understand that they're there. They don't have to babyfoot you around every step along the way when it comes to molecular structures, and this is one of those examples. So there's hydrogens here, and if there's hydrogens here, there's a possibility of a NMR signal coming from them, because that hydrogen's attached to a carbon, and that hydrogen could be different than the next door hydrogen or the 2 hydrogens down from that. So there are more signals than 2. So I'm going to do it all over again. I'm going to go and then I'm going to draw a bromine that is here. All right. So I'm going to go back and I'm just going to start with the original structure. And that original structure was a CH3 group on the end, CH2, and the benzene. So I'm now going to take one of those hydrogens off of the benzene and substitute that with the bromine. And then I need a question, is this a different structure than the other 2 that I've drawn? So I've got check on the first one, check on the second one, and I'm going to do a check on the third one. This third option is a different signal. And the reason is because this bromine on the ring is different than the bromine in the middle on the ethyl group and the bromine here on the end on the ethyl group. They are all in different positions and they will be called a different name. So there is a third signal. And then you're going to look at this and you're going to go, okay, well, I think we're kind of coming to a close, because what I'm seeing here is the benzene ring, and then I'm going to put that hydrogen on the benzene ring, and then I'm going to write a bromine group there, and I'm going to say, well, you know what, that bromine is on the benzene and that bromine was on the benzene, so those hydrogens are equivalent. No, that's wrong. They're not equivalent. And the reason is because, go back to naming. Please go back to naming. Because if you named this, you would see that this ethyl group and this bromo group, OMP, you know me, right? You remember those lectures? It's all coming back. It's all coming back to me now, Celine. All right, so here this bromine group is on the benzene ring, and this ethyl group is on the benzene ring, and they are M to each other. So that would be an M position here. Well, the problem is that if the bromine was on that position with that hydrogen the first time that we did it on the benzene, that is not an M position. That is a OMP, you know me, that is an O position instead. So that also means that if I get rid of that bromine and I get rid of that hydrogen to go back to the normal state and put my bromine here, yes, that bromine is on the benzene, just like the 2 other ones. But this is different because you've got to name it different. It is a 1,4 position or a para position here. The other time it was a 1,3, and the other time it was a 1,2, but now it's a 1,4. They're all different names, and if they're all different names, they're all different signals. Got it? That's how NMR works. So what this means is that I get a signal from that hydrogen set, a signal from those hydrogens, a signal that's different from that hydrogen because that is the ortho position. This one is going to be different because that's the meta position, and this one's going to be different because it's a para position. Now, if I keep going on around the ring and I that hydrogen and I replace that with a bromine, That's not a big deal because that also is the meta. We've already taken care of the meta. That's going to be the same name as the meta from up above it. No difference. The same thing's going to happen to the bottom hydrogen. That hydrogen is ortho. So that hydrogen has already been taken care of. These two hydrogens are equivalent to each other. So therefore, they will be the same signal. These two hydrogens are equivalent to each other. So therefore, they will provide me the same signal. However, the purple boxed hydrogens, the burgundy boxed hydrogens, and that bromine that's out there right now in the para position, they will give me different signals. So the answer here, how many different signals would you get from this compound? The answer is 5. 5 in total. That is what we're after. All right? Okay, so we need to do more of these. We need to go through and we need to learn some more of these tricks so that way I don't get tricked when it concerns these questions that they might have for me as far as how these signals are going to relate to the structures. So some of these we've done before. Great. Good review. Others we're going to look at for the very first time. So let's say that I have an example problem. Example. All right, CH3, CH2, CH2, and Br. How many signals do the NMR give me? Okay, so I need to look at the number of signals. Bromine's actually already here. I did not a hydrogen and put a bromine there, right? Bromine just comes along with the structure. That is the compound that we want to analyze and that we want to run. So again, if this is bothering you, I would take the extra time until you really get it in gear, folks, to just draw the different versions of the structure and go through and start naming these. And if you get a different name, then you're going to end up with a different signal. So in the first example, I'm that hydrogen and I'm replacing that with, I don't know, something. Let's just put an OH group there. I don't care what it is. Just put a group there. And then in the second one, I'm going to, and then I'm going to put the same group here. And then in this one, I'm going to, and that goes from a 3 to a 2. And then we also have the group here. Now, I chose OH. You could choose another bromine. I don't care what you do. As long as you know which bromine that you've added on and how you compare them, that doesn't really matter. So I could do a bromine, I could do a chlorine, I could do any group that I'm comfortable with as far as nomenclature. So now the question is, how many different signals do I get? And in other words, do these provide me different names? And I hope that you can look at this without naming them. And I hope that you can just immediately say, yes, based on what you taught me this semester with alcohol nomenclature and alcohol reactions, they are all 3 different names. And because of that, they all 3 give me a signal. Because this is the first carbon. And that would be 1, 2, 3, prop. And this would be a propanol. I'm not going to worry about anything else. This one, 1 carbon, 2 carbon. That's a second carbon. That's where the OH group is here. So I would look at this and I would say, oh, well, if I look at this thing, this is a 2 propanol. All right, so don't have to name anything yet. It's just completely different already. And then if I look at this one, you're going to look at it and go, whoa, 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 whoa. This OH group is on the end. So that is the first carbon here. And the answer is, yeah, you are correct. This is a propanol structure all over again. And you would say, well, the first one and the third one's the same. And I would say, no, it's not, because you got a bromine there as well. So this one, that bromo group that is currently already there at that structure, this is a 1 bromo propanol because that OH group makes that carbon spot 1. This third one, though, that was our option. Well, this OH group is on the end. That forces that one to be the first carbon, which means that on the third carbon here, that is where I would have the bromo group. So they are all 3 different. And you can just visually compare the structures and know that they are different structures. And because of that, this one would have 3 signals. It would have a signal from this carbon, it would have a signal from that carbon, and it would have a signal from that carbon. And I'm saying carbon because that is what houses the hydrogens. So let me rephrase it. This NMR, it would give us a signal for these hydrogens, 2 of them that are equivalent. Then it would give us a signal from these hydrogens, which are different than the previous, but 2 hydrogens are equivalent there. And then this one would be our 3rd signal, and that would be 3 equivalent hydrogens from that particular signal that we get. That is how we do this, all right? Okay, maybe you're getting a little bit more comfortable with these. So let's test it. All right, CH3, CH, CH3, and a bromo. All right, how many signals? This time, I'm not going to a hydrogen. You can do that on your own, and I want you to make that sound effect when you do. So what we're going to do here with the NMR is we're just going to visually look at this and say, how many different hydrogens are there? How many signals are we going to get? So I hope that you can look at this and say, well, first off, this carbon in the middle has a hydrogen. That hydrogen is going to give us a signal no matter what. So this is one signal that we're definitely going to get. And then I look to the left and then I look to the right, and I see both of those carbons having 3 hydrogens. And those hydrogens are basically in a symmetrical position, right? Meaning that the hydrogens here on the left, that is on a carbon that's attached to one other and a bromine. And then if I look to the ones on the right-hand side, these are 3 hydrogens on a carbon that's attached to one other as well as a bromine. So these things would be equivalent, meaning if I did and I put a 2 here and put another bromo group there, I can do that. It doesn't have to be anything special, anything that I'm comfortable with. And I name it. I would get the same name as if I did it here to the left as if I did it there to the right. It would end up being a 1,2 dibromo, no matter how we look at it, right? This would be the 1 and 2 position, and if I did it over here and not to the left, then that would force that carbon on the end on the right-hand side to be number 1, and the carbon in the middle, number 2. So no matter what I do, I'm going to get a 1,2 dibromo if I go through the mess of making these names. All right, so what that means now for us is that the 2 end carbons, these would be equivalent. So that means that those hydrogens that carry with them are also equivalent. So I only get 2 signals here. That is it. And the reason is because this CH3 group and this CH3 group are equal. They are the same signal in the NMR because they're the same protons in the NMR. So I would get one signal that would basically relate to that one hydrogen, and then I would get another signal that would relate to both of those carbons, the one to the left and one to the right. And that signal would represent 6 equivalent hydrogens in the molecule, 3 on the left and 3 on the right. So 2 signals for 2 bromopropane. All right, we'll do another. And this time, we'll look at CH3, CH2, O, CH3. Now do it all over again. Nothing special, right? I mean, I'm going to visually look at this and I'm going to say, all right, well, first off, before I do the blup, I'm going to see a signal from here because that has 2 hydrogens, that carbon has 3, and that carbon has 3. So I know that this automatically is going to be different. I mean, there's no if, ands, or buts about it. It's going to be different because there's a different number of hydrogens on the carbon. All right, so there's one signal. Now I need to look at these two CH3 groups and determine, are they the same or are they different? And I don't have to the bromine and replace it, blah, 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 because only thing I have to do is look at in relation to, meaning that the carbon to the right-hand side with those 3 hydrogens on the right, on the end, this next door neighbor is an oxygen, right? And these carbon, or that carbon to the left with those hydrogens on that carbon, well, next door to it is a CH2, and then next door to it is an O. So those hydrogens are different. And if we did the hydrogen and put a bromine on it, we would get a different name depending on if we chose it to the left or if we chose it to a right. That's because these hydrogens are in different positions according to that oxygen in that ether group. And I hope that you remembered that was an ether group. So we get a signal from this one, and we also get a signal from this one. So we're going to get 3 signals here. This signal is going to come from 3 hydrogens. This signal will come from 2 hydrogens. And this signal will also come from those 3 hydrogens. And they are all different because they're in different positions within the molecule. All right. Now let's do another. We'll do CH3, O, and CH3. Keeping the same thing in mind, how many different signals do we get with the NMR? So if I look at the oxygen here, I'm going to get no NMR because we're talking about hydrogen NMR. We're not talking about anything else. And that poor little low oxygen in that ether functional group, it doesn't have no hydrogens. And because it has no hydrogens, I'm not going to get a signal, am I? So I get signals to the left and I get signals to the right. And I need to see, are they the same or are they different? All right, so that means I'm already going to go cha-ching. We get one there. There's a signal, CH3 group to the left. And then if I look at that molecule and go to the right-hand side of that oxygen, I'm going to see another CH3 group. It's the same. I don't need to go through and the hydrogen and put a bromine on it. It is the same type of hydrogen on that carbon as it is to the one on the left. So that means these two things are equivalent to each other, because if I did replace the hydrogen with a bromine and I name it, I would get the same name whether I did to the left hand or whether I did it to the right hand one. There's no difference. So I get one signal in the NMR, and this one signal is going to include those 3 as well as those 3. So a total of 6 will be represented in that signal that I get from the instrument. Hopefully you see what I'm doing here. I'm building it up very, very slowly for you. That's what we want. We want baby steps. All right, so that's where I'm going to stop. In the next video, we'll do more examples. We'll continue with this idea. We'll keep looking at these structures, and we'll keep identifying the total number of signals from an NMR.